Next speaker is Professor Michael Bronstein. So let me just quickly introduce you. You already know him probably. So he's a professor at Imperial College London, where he holds the chair in machine learning and pattern recognition and head of graph learning research at Twitter. Dr. Bronstein received his PhD from the Technion in 2007. He has held visiting appointments at Stanford, MIT, and Harvard, and has also been affiliated with 3 institutes of advanced study, TUM as a Rudolf Diesel Fellow, at Harvard as a Radcliffe Fellow, and at Princeton as a short-time scholar. So Professor Bronstein is the recipient of Royal Society Wolfson Research Merit Award, Royal Academy of Engineering Silver Medal, 5 ERC grants, 2 Google Faculty Research Awards, 2 Amazon AWS ML Research Awards, among others. So he's a member of the Academia Europa EA, Fellow of IEEE, IAPR, BCS, and LS ACM Distinguished Speaker, and World Economic Forum Young Scientist. So in addition to his academic career, Professor Bronstein is a serial entrepreneur and founder of multiple startup companies, which have been acquired by Intel and Twitter, among others. So Professor Bronstein, over to you.
Thank you very much. Thank you for this introduction and for the invitation to speak here. So I hope you can see and hear me well. So I would like to talk today about maybe somewhat different view on graph neural networks. As you probably know, they have become very popular in many fields, including natural language processing and processing of social network data and chemistry and structural biology, just to mention a few. And I think it's interesting to think, well, to me at least, when I think of about explainable or interpretable AI, right, or machine learning, I think one of the probably first steps towards this is to try to put them on solid mathematical foundations. And this is what I will try to do here, at least to present some links that are probably less known or maybe slightly more surprising in this community. So let me start maybe with a broad quote or claim. So first quote is from Hermann Weyl, a mathematician. He was writing that symmetry, as wide or as narrow you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And the second quote is from Philip Anderson, a Nobel-winning physicist. He said it even more briefly. It is only slightly overstating to say that physics is the study of symmetry. So symmetry is really fundamental. And we can see that it was a driving force that unified geometry in the end of the 19th century, the famous Erlangen program of Felix Klein. And similar ideas can be used and reapplied to in the field of machine learning to try to unify the zoo of different architectures for different use cases and for different data. So this is what we try to do in our book on geometric deep learning, try to derive some of these popular architectures from first principles. And if some of you might have seen my keynote talk at ICLEAR this year, I will not repeat it. I will just briefly recap it here. And you can see some more details about this Erlangen program of machine learning on the website geometricdeeplearning.com. So if you think of supervised machine learning as a kind of black box that interpolates the function that maps you from the input to the output, one thing that you can do in order to cope with phenomena that complicate this problem in high dimension, namely the cursive dimensionality, is to try to leverage geometric structure of the data. And that's what we call the geometric deep learning blueprint. And essentially it consists of looking at 3 different objects. So one is the domain on which the data is defined, and it's convenient to think of images. So images are not just multidimensional vectors, they come from a 2-dimensional grid. So they live on some discrete 2-dimensional domain. So there are signals on this domain. And then when we, for example, want to classify images, we apply a function to signals on this domain. So we have the domain omega, we have signals defined on it, and we have some function defined on these signals. So the structure of the domain can be modeled by the symmetry group. for example, the group of translations in the case of images. It acts on signals on the domain through the group representation. Again, in this example, it would be the shift operator. And then we can impose the structure of the group through some prior that we call invariance or equivariance on the functions that are defined on this signal. And again, just to give you a very clear and very familiar example, convolutional neural networks are a very famous instance of this blueprint. So we have the translation group, the shift operator, and the shift equivariance, which is manifested through convolution or convolutional layers in convolutional neural networks. Another interesting example are graph neural networks, where the symmetry structure is the permutation group, coming from the fact that we don't have a canonical order of the nodes in the graph, and then it acts on the node feature vectors through the permutation matrix, and then permutation equivariant functions are, for example, a message passing mechanism that is commonly used in graph neural networks. So you can see that this is also an instance of the same blueprint. Now, these ideas can be applied to different domains. We can apply them to grids, for example, right? We can apply them to graphs, as I mentioned. We can apply them to meshes. So these are techniques are popular in computer graphics. And one thing that you notice that all these domains do have some continuous analogy, right? So in the case of a grid, for example, we can think of it as a discretization of the plane. When we have meshes, we can think of them as discretization of two-dimensional surfaces or manifolds. We don't have this continuous analogy for graphs. And to me, personally, this is very disturbing. So we would like to answer this question: what would be a continuous model for learning on graphs? Now, if we look at the way that graph neural networks are typically implemented, it is a form of local aggregation. So I look at a node in the graph, I look at its neighbors, I take the feature vectors of the neighbors, and I put them together. So together they form what is technically called a multiset, because features can appear more than once, so it's a multiset or a bag. Together with the feature vector of the node itself, we need to aggregate them, and I remind you that because we don't have a canonical ordering of the neighbors, this aggregation must be permutation invariant. So we must apply some symmetric function to these inputs. And this is how typically graph neural networks are structured. So we have some permutation invariant aggregator, we have some learnable function that applies to it, and we have some set of weights that can either depend only on the structure of the graph, or they can also depend on the features themselves. And it can be shown that the sum, the obviously far more mostly used aggregation function, is sufficiently expressive. We'll talk about it in a second. So we can use learnable coefficients. This is the attentional flavor of graph neural networks, or we can use a general nonlinear function. In this case, we get the message passing graph neural networks. And we can also augment it with positional encoding. So the attentional flavor is very commonly used in transformers, in natural language processing applications, where we do actually have an order of the tokens that come in a sequence. So usually this order is captured by positional encoding that attaches some descriptor to every node in this graph. Now, when we apply this kind of aggregation at every node of the graph, we get a permutation equivariant function. So if I change the order of the input nodes, the output will be changed in exactly the same way. And it appears that the choice of the aggregator is very important, and it was shown that message passing graph neural networks, where the aggregator is injective, are at most equivalent to the Weisfeld-Lehmann graph isomorphism test. So it's a classical algorithm in graph theory that tries to determine if two graphs are structurally similar, if there is an edge-preserving bijection between them, called isomorphism. And the way that it works, it's iterative color refinement technique. So it starts with a graph where the nodes are labeled in the same way. So when I say color, I mean discrete label. And then I apply an injective function. You can think of it as a kind of hashing that changes the color of the nodes. And here you can see that initially we have two types of neighborhoods. So we have a blue node with two blue neighbors and a blue node with three blue neighbors. They will be colored differently in green and yellow. We can apply this procedure again. Now we have three kinds of nodes, and at some point the color will stop changing. So at this point we'll output a histogram of colors. And if I give you another graph and I do the same process for this graph and I get a different histogram, I can guarantee that the graphs are not isomorphic. But if I get the same output I actually don't know for sure. It's a necessary but insufficient condition, and you can find examples of not isomorphic graphs that would be not distinguishable by this coloring procedure. And you can also see why, because if you look at every node, what it sees essentially is a kind of rooted tree or a star shaped graph around every node. And in these graphs, for example, these will be completely indistinguishable. So what is commonly done is, as I mentioned already, using positional encoding that somehow pre-colors the nodes, and you can see that with the use of positional encoding, we can easily distinguish between these differently structured graphs, and this increases the expressive power of graph neural networks. And there have been multiple ways of doing positional encoding. You can, in the simplest case, use even random features. You can use, for example, the eigenvectors of the graph plus an operator. You can count substructures such as cycles or paths or clicks, or even use aggregations of bags of subgraphs. But I think we need to be honest, we have no idea what is the right way of choosing the positional encoding. So we want to do something that is more principled and more formal. And finally, another thing that we see often in graph neural networks is this phenomenon of over-squashing and bottlenecks. And it has to do with the fact that in graph neural networks, the graph is both part of the input and the computational structure. So we basically propagate information on the graph. And if we are unlucky in the sense that the graph is structured such that its volume grows exponentially, so we have a lot of nodes that if we go 1 hop or 2 hop or 3 hop, so the volume grows too fast with the radius, and we also, our problem depends on long distance information, so I need to propagate information from distant nodes, and we have too many of these, we get the phenomenon of over-squashing that I need to squeeze a lot of information into a single feature vector. And empirically it was shown that graph rewiring, basically changing the graph on which to propagate information, helps with the phenomenon of over-squashing and bottleneck. And again, multiple methods have been proposed, but we don't have a clear recipe how to rewire the graph. So we would like to give a principled view on this problem as well. So this is what I will try to present today in the time that I have. So some continuous model for graphs, a principled view on positional encoding, and if time remains, also how to do in principled way graph rewiring. So let me start with a continuous model, and this is our recent paper from ICML on neural diffusion on graphs. So diffusion processes in general are pretty old, so they have been studied in various fields of science for centuries. Probably one of the first or the early principled studies of diffusion, of thermal diffusion, was done by Isaac Newton. Sir Isaac Newton, he published in 1701 anonymously a paper in the Proceedings of the Royal Society about measuring temperature, and that's where he described what nowadays is called the Newton law of cooling, stating that the temperature of hot body loses in a given time is proportional to the temperature difference between the object and the environment. So it's a kind of global behavior. And well, it was a kind of hodgepodge of terminology because he used the term calor, which in Latin literally means heat. And now we understand by heat something completely different. So the right term would be temperature, that was yet to be invented. So the next step was done by Fourier, that derived what today is called the Fourier heat conduction law, that already formulates it in terms of differential calculus, stating that the heat flux resulting from thermal conduction is proportional to the magnitude of the temperature gradient and opposite to it in sign. So it's already some local differential rule, and the final part of it is due to Fick, who studied chemical diffusion, and he said that temperature change in time equals to heat flux through volume. So it's a kind of conservation law, and now putting all these things together, we can write what is called the diffusion equation. So if you think of different temperature in some domain, basically the temperature gradient creates the flow of heat, the heat flux, that is inversely proportional to the negative gradient of the temperature. And Fick's law is a conservation condition and tells us that no heat is created or disappears, so the change in the temperature is only due to the heat flux. So basically together this gives us the diffusion equation. The left-hand side is the change in time, the right-hand side governs the spatial behavior of the temperature. And in the simplest case, when the property of the medium are such that the heat flows equally in the same, at every point in the same direction, we have constant diffusivity. This is what is called homogeneous and isotropic diffusion. And we can interpret it either as the gradient flow of what is called the Dirichlet energy, right? So it's kind of minimization process of this energy, or we can even write it in closed form solution as convolution with the Gaussian filter in the Euclidean case. We can also consider more interesting forms of diffusion where the diffusivity is position dependent. So this is called non-homogeneous diffusion, or is also direction dependent. This is called anisotropic diffusion. And the non-homogeneous case attracted a lot of attention in image processing, where it was shown that you can apply this diffusion process to an image, and if you choose the diffusivity function in such a way that it discourages diffusion across discontinuities in an image, basically you don't diffuse across edges, you get nice image denoising that doesn't destroy the structure of the image. So that was the seminal work of Pietro Perona and Jitendra Malik from the 90s, and it had a lot of follow-up in the image processing community. And here you can see an example, the portrait of Sir Isaac diffused with the standard diffusion, convolution with the Gaussian, and this nonlinear diffusion that removes the noise but nicely preserves the discontinuous structures. So we can apply the same ideas to graphs. Basically, we have immediate formal analogy between all the operators that we defined in the plane on the graph. So we can define the gradient as the difference between the features in a pair of nodes connected by an edge. Divergence will be the sum of features of the neighbors of a node, and these two operators, same way as in the continuous case, are formally adjoint. And we can define the Laplacian operator, that is the divergence of the gradient, or we can think of it as the difference between the features in a node and its neighborhood. And this is how the diffusion equation looks on graphs. So it has exactly the same structure as before. This is our discrete graph gradient. This is the diffusivity function. So we'll see that immediately that we can interpret it as attention in graph attention networks. And we will assume that it's normalized. And this is our divergence. So it has exactly the same structure of divergence of gradient scaled by something. So in order to solve this equation, we need to use numerical solvers. Usually it doesn't have closed form solutions. So standard way would be to discretize it. And we can discretize it with explicit or forward Euler discretization, basically taking forward differences instead of the continuous temporal derivatives. And this is how it looks like. So I can rewrite it in matrix vector form. And this is how it looks like. So one thing that you notice is that the matrix here that represents how the next iteration looks like has exactly the same graph adjacency structure. Usually it is sparse. Another thing that we can show, this is standard exercise in partial differential equations, that this scheme is stable if tau is sufficiently small. So explicit schemes are usually stable only with small step size. We can also see that it is equivalent to graph attention network if we assume no nonlinearity and a step size of 1. So in this case, the diffusivity is exactly the attention function of the gut neural network. And of course, we can use other more interesting schemes. So here's a semi-implicit or backward Euler discretization, where we take a backward time derivative. And here we get a system of equations where we need, in order to compute the next iterate, we need to solve a linear system or invert this matrix B. And now this matrix B will not necessarily be sparse. Actually, in most cases, it will be dense. And this is analogous to a multi-hop filter. Basically, I'm not looking only at my neighbor nodes. I need to look at information from multiple nodes. The advantage of this scheme, of course, that it's unconditionally stable. So I can take tau as large as I want. And this is just one example. There is a plethora of literature in numerical analysis of different explicit or implicit schemes that use multiple steps, adaptive step size, and so on and so forth. So we can really leverage a lot of this theory and implement a learnable diffusion process that we call graph neural diffusion or GRAND. So in this case, we solve this diffusion equation where the diffusivity function is parametric and the parameters are learned for a specific task. What is interesting here is that we specifically choose to work with time-independent diffusivity function. So in the language of neural networks, it means that we have parameters that are shared across layers. Every layer has the same set of parameters. And this dramatically reduces the numbers of parameters. As I will see in a few seconds, it's actually a big advantage. So what do we gain from this? You can see that this is just maybe some vain exercise. First of all, we get a new perspective on old problems, like the problem of over-smoothing in graph neural networks, the problem of bottlenecks. It also yields new architectures. So first we can formalize some existing architectures as a discretized graph diffusion equation, but we can also leverage more efficient solvers such as multi-step adaptive or multi-grid solvers that do not have immediate analogy in the graph neural network architecture world. So I think this is just the beginning of a new generation of architectures. We can also get some theoretical guarantees about stability convergence, so something that has been, I would say, quite direly lacking in graph ML literature, and also deeper links to other fields that are less known in machine learning, such as differential geometry and algebraic topology. So many of these things are related to these topics, and I'm not sure I will have sufficient time to talk about it. So here's one example. One of the difficulties, for example, that are well known for graph neural networks, that it's difficult to create a deep graph neural network architecture. We see different phenomena such as over-smoothing. So when you add more layers, then the performance degrades. So in this case, we don't have the depth in the ordinary sense of the number of layers in deep learning. Here, the analogy of depth is the diffusion time. And if you use simple explicit scheme with fixed iteration step, we can think of the number of layers, right, as the number of iterations. Basically, we divide the diffusion time by the time step. In adaptive schemes, we can have bigger steps, meaning that we have less layers, but the layers do something else. And in implicit schemes, we can trade off depth versus width, basically the number of hops that we take in the graph. And well, these are some benchmarks on standard data sets that are used in the community. So the method performs better or on par with other methods, but maybe have a look at the difference in the number of parameters. So the standard GATT architecture uses more than 1.5 million parameters. Here we use less than 100,000 parameters. That's exactly because of these shared parameters that I mentioned in the beginning. Now, what is still missing here is that we look so far at the discretization of the time, which is somehow is pretty easy, but we didn't look at the spatial domain, right? And if we take a step back and think of diffusion in the plane, the way we discretize it is really up to us, right? So if you take a grid, for example, and you have isotropic diffusion, so we have the Laplacian operator, you can discretize it any way you want, right? So any of these numerical stencils will work, right? Or any combination of them because of linearity. So we really have a lot of flexibility in how we discretize continuous differential operators. Can we do something like this on graphs? And this is the idea of graph Beltrami flow. So this was our paper we presented last week at NeurIPS. And the idea is to look at this anisotropic diffusion in a different way. So before that, we had a nonlinear diffusion where we have the diffusivity function that adaptively told us to run the diffusion faster or slower, or maybe stop it completely. An alternative way is to look at the image as an embedded surface, and we have a non-Euclidean version of diffusion on this surface where we replace the Laplacian with what is called the Laplace-Beltrami operator. So it's a non-Euclidean differential operator. So more formally, we consider the image as an embedded two-dimensional manifold. So in case of, for example, an RGB image, you can think of it as a two-dimensional surface in R5. So we have the geometric coordinates, right, and or the positional coordinates and the feature coordinates. So the positional coordinates will be, in this case, U1 and U2, right, the X and Y coordinates, and the feature coordinates will be R, G, and B channels of the image. Okay, and we can define, thinking of it as a manifold, we can define a metric on this manifold by the pullback from the embedding. And the Beltrami flow is a gradient flow of a special energy that is called the Polyakov functional. So it's an harmonic energy of the embedding, and it's very popular in some fields of physics, such as string theory, where it can also be explained. Basically, it's a geometric theory that gives rise to certain properties of particles. And this is how it looks like. So we can also think of it as a generalization of the Perona and Malik scheme, where the diffusivity function comes from the Riemannian metric of this manifold. So we can apply exactly the same idea to graphs, and we can formulate the Beltrami analogy of Beltrami flow on graph, where now we have a pair of coordinates for each node. So we have the positional coordinate and the feature coordinate, and we evolve both. So we have evolved both. We do the diffusion of the features of the graph and the diffusion of the graph itself. And now you see that we don't really have a graph. The graph is replaced by the positional coordinates, so we can rewire it as we like. So if the nodes, the positional coordinates change and they move, we can adapt the graph on the fly. And probably it's one picture is worth 1,000 words. So here you can see the standard Cora graph. So this is a citation network. So here the nodes represent papers. The colors represent well, some low-dimensional embedding of their features, and the positions of the nodes represent the positional embedding, again some low-dimensional projection. So you can see that as we evolve, as we run this diffusion equation, both the features diffuse as well as the positional coordinates, and the graph is rewired on the fly. So we change the graph as the positional coordinates change, and you can see that many graph neural network architectures can be interpreted as particular instances of this architecture. So it is indeed very general and very broad. And of course, it produces better results. But I think what is probably most interesting is that it gets this interesting link to differential geometry that is a little bit exotic and probably less known in machine learning, even though judging by this year's new RIPs, there are many more papers that try to introduce geometric models in ML. So I will finish. I will not. I don't have time to go into too much details about this other paper, but basically this idea that you do something on a domain that moves under your feet in some sense might be very exotic in machine learning, but it's very common and very standard in differential geometry. And one particular celebrated result or set of tools that are used in differential geometry is what is called the Ricci flow. So the Ricci flow is a kind of evolution of the metric of the manifold. So it's a partial differential equation that structurally looks like the diffusion equation. So we have the temporal derivative of the Riemannian metric on the left side, and we have the Ricci curvature. Basically, it's a second order derivative, second order operator, if you think of it, of the manifold. And basically, by making this evolution, we change the manifold itself. So this is how a manifold that looks like this kind of a dumbbell would evolve under the Ricci flow. So here the colors represent positive and negative curvature. And the Ricci curvature was named after Gregorio Ricci Curbastro, an early Italian differential geometer. The concept itself was introduced by Richard Hamilton as a way towards proving the Poincare conjecture, and it was used in a successful way by Grigori Perelman about 20 years ago in what science declared as the breakthrough of the year, the proof of the Poincare conjecture. So this technique, or more specifically Ricci flow with surgery, was used to prove this 100 plus years old result in differential geometry. So what does it have to do at all with graph neural networks? And again, let me mention the oversquashing phenomenon, which is the failure of message passing to efficiently propagate information in a graph due to some structural characteristics that are called the bottleneck. And as I mentioned, it occurs in problems where we have long distance dependencies that require information from nodes that are k hops away. And a good example is application of graph neural networks in chemistry, where you have a molecule that maybe the properties of the molecule will depend on atoms on two different sides of this graph. So we need to propagate information from these nodes, from these atoms on the graph, and it might be difficult. So we also see it acutely in graphs with exponential volume growth, right, where you have too many neighbors, and it tends to deteriorate with the depth of graph neural networks. And it is empirically alleviated by graph rewiring. So what we try to do in this paper is formally define oversquashing. relate over squashing to structural characteristics of the graph that are manifested geometrically through negative curvature. So we need some definition of what is meant by curvature of a graph, and then an algorithm that rewires the graph in a way that is similar to Ricci flow, that makes just a few surgeries to alleviate these bottlenecks. So I think I probably have something like 5 minutes, so let me just briefly overview these results. So the way that we think of over-squashing is a kind of sensitivity analysis. So if we think of a message passing type graph neural network, basically at some layer L+1, we have the dependency on the neighbor nodes, the features produced by the previous layer. So if we apply it multiple times, we can trace back the influence of the input, right? So what we want to say is how sensitive is the feature produced by some layer of this graph neural network at node I to some source node that is geodesically r distant from this node. So I have a node that is a few hops away. I change the input feature vector. I want to see how the output of the graph neural network at the distant node is influenced by this change. So it's standard sensitivity analysis. It is given by the Jacobian of this equation. And you can see that we can write a bound. It depends on the properties of the activation functions, but also on the adjacency matrix of the graph. So the graph structure enters here in some way that it is not very explicit, right? So it's not very clear. Basically, it's some power of the matrix, right? So basically, it hides some structural properties of the graph here. So pathological example is a binary tree, right? So in a tree, the dependency decays very fast exponentially with how deep we go in the tree. So this is probably the worst example that can happen. Now, a standard, basically what we expect to see here is that something that looks like a grid will behave nicer than something that looks like a tree. And the standard way in differential geometry to distinguish between things that look like a tree, right, or a discrete or continuous analogy of it, something that looks like a plane, is curvature. So curvature can be defined in many ways, but one way to think of it is if I take two nearby points and I send geodesics at the same velocity from them, what happens to them? Whether they will converge, and in this case we locally look like a sphere, they remain parallel. In this case we're flat, we locally look like a plane, or if they diverge. So in this case we have hyperbolic geometry. So this can be measured by curvature, and in the first case we have positive curvature, in the second case we have zero curvature or flat curvature, and in the second case we have negative curvature. So this is something that looks like a saddle surface. So this analogy of geodesic dispersion can be also applied to graphs. And in a graph, if we take two nearby nodes, right, that are connected by an edge, if we see that basically edges that are shot from these 2 points, two nodes tend to form triangles, we have something that looks like a sphere. So a clique is an analogy of spherical geometry in the discrete case. If they remain parallel, right, they form rectangles, so we get something that looks like a grid. And if they don't form anything, right, if they become further away, then we have something that looks like a tree. This will be the discrete analogy of a negatively curved surface. So we can define, well, let me not go into the details, an analogy of Ricci curvature for every edge of the graph that is computed locally, combinatorially, just by counting the number of these low-level structures. So there are multiple definitions of something similar to the Ricci curvature on graphs, so particular to constructions due to Olivier and Foreman. So we have our own construction that behaves similarly to the continuous case. So for example, cliques will be positively curved, grids will have zero curvature, and trees have negative curvature. And we can also relate it to the well-studied curvature, such as the Olivier curvature that is related to optimal transport. So our curvature is a lower bound on it. And we can show, for example, that when our graph is positively curved, then the volume growth is polynomial, as again we expect in the continuous case. And the main result is, again, let me abstract out the details, is that we can relate over squashing to curvature. So what we show is that if the graph is negatively curved, then basically we have an upper bound on these Jacobian. So in other words, we have limited sensitivity the graph neural network, or in other words, over-squashing can be attributed to the negatively curved edges. So that's the main result of the paper, and we show a process that is similar to backward Ricci flow that surgically removes or adds edges in the graph to alleviate these negatively curved edges. So we also show that we can relate it to spectral properties of the graph, and in particular, an important property that is called the Chigger constant. And we also show that diffusion-based approaches for graph rewiring do not necessarily improve graph bottlenecks. And this is particularly acute in the heterophilic case, where the neighbors of a node are not necessarily similar to the node itself. Basically, diffusion-based approaches tend to connect, tend to create new connections in a part of the graph that is already strongly connected. And in case of heterophily, this can create disasters. And in fact, this is confirmed experimentally, that in the case of low homophily, these methods do not perform well, as opposed to this surgical Ricci-inspired method. And also, we touch much less the graph, exactly because of this property. So this is an example of a graph that we try to rewire. So diffusion-based rewiring changes it dramatically, whereas in our case, the changes are only negligible. So let me conclude it here. So I hope to have shown, maybe a little bit briefly and a little bit rushingly, some links between graph neural networks, differential geometry, and partial differential equations. So it's really a new set of powerful tools that previously have not been well known in this field to study problems in GraphML from different perspectives. It also allows, in particular in these works, to take principled position on some architectural choices that so far have been mostly empirical, such as positional encoding, graph rewiring, and I think it's just the beginning. There might be many interesting follow-up works, and there are still many interesting open questions in this field, but it is probably one of the first mathematical passes towards better understanding what these methods do. So I will stop here. Thank you very much for your attention.
Thank you, Professor Bronstein. So I open the floor for questions. So if you have any questions, please write them down in the QA panel in Zoom, and I will relay it to Professor Bronstein. And the panelists, if you have any question, please unmute yourself and ask.
Hello. Yeah, so thanks. This is a fascinating talk. Yeah. So I have a small question, is that when you are in order to try squashing, you are doing the graph rewiring algorithm. You are doing some sort of graph rewiring. So and which also takes care of long range relationships, which you are telling that it can also take care of. But won't this graph rewiring also destroy some of the relationships, existing relationships, and how would that effect be?
Yeah, it's a very good question. So and again, I alluded to it, but maybe I should state it again. So one of the difficulties or subtleties in graph neural networks that a graph is both a computational graph and the input graph. So the graph contains both information about your input data. It's part of the input data together with the node or edge features, as well as it is used as a mechanism to exchange information. Now, what was shown in several works that you can depart safely from this graph to do exchange of information. To which extent it's not clear. So that's why graph rewiring. Basically, we try to change this graph as minimally as possible. But what probably should be done really and in a better way, you should probably start with the diffusion without touching the graph, and then change the graph somehow down the road. So basically, you can think of two coupled diffusion equations, right? Or two coupled processes, one diffusion on a given domain, another one the diffusion of the domain itself, like in the Ricci flow, and some way of coupling these two differential equations. And they can evolve at different speeds. So the diffusion can happen at faster speed, whereas the evolution of the domain, the diffusion of the graph itself, can happen at a slower speed, and basically the relative speed can be learned and dependent on the application.
Oh, okay. Okay, great. Thank you. Yeah, I understand. Yeah.
So we have a question from the audience as well. So when a graph is rewired based on curvature, what happens to the graph in terms of the edge connections? Does information stored in the graph change?
Right, it's a good question. So, so far we didn't consider, so I think two caveats. So this is probably, I wouldn't take this work as a practical advice. I think it's more basically giving a new view of a problem. So I think this kind of rewiring is not necessarily the right thing to do. So we consider the graph where that is unweighted. So we didn't consider weights. Weights are easy to incorporate. Edge features are less easy. And we also, the definition of the curvature doesn't take into account the features. So basically, we can link it to the previous version, the previous talk about Beltrami flow, where we consider a joint embedding of the graph in positional and feature space, and we can easily define a curvature that depends on both. So in my opinion, we must take three things into account when designing efficient graph neural networks. One is the data, basically the features. The second is the graph, and the third is the task. Because depending on the task, we might get, we might want to use a different graph, right? So one task, for example, might depend on the local information. So in this case, we don't really care about these bottlenecks and over-squashing. If on the other hand, we have a task that depends on long-distance relations, and it can be a task on the same data set, then maybe we'll need to do something to the graph. So I think it's a kind of elusive answer where it depends, right? So it depends on what you're trying to do.
Okay, there is another question. So what happens when nodes and edges get added to the graph? So if the graph is changing, I mean, new nodes and edges are getting added, so how do you deal with that?
Yeah, well, so it's a good question. So I'm not sure that I completely understand the questions. Basically, it can be answered in different ways. But one of the differences, let's say, in the GraphML applications is the difference between inductive and transactive settings. So in transactive setting, you know the graph, and maybe you don't know the labels of some of the nodes, and you try to get the labels, but you have access to always to the structure of the graph. In the inductive setting, which is probably more difficult and more practical, imagine that you have a social network where a new user comes, right? And this new user maybe creates new connections, but you want to make predictions to this new user that has never been seen before in the graph. So the graph itself evolves. And in this case, there are many other architectures. We also worked on this. For example, we had a paper last year where we consider also the temporal aspect. So we consider dynamic graphs that are given as a stream of events that add or remove nodes or edges. It is interesting actually how this physical time can be related to the pseudo time of the diffusion. So we have some kind of dynamically changing domain and also some dynamic process that happens on this domain, right? The information propagation. So there might be some interesting links to optimal control theory. So I've seen a few papers that try to look at graph neural networks from that perspective.
Okay, maybe one last question. So do you consider the graph here to be undirected or directed?
So it doesn't really matter. It can be directed or undirected. So for the diffusion equation, yeah, usually, for example, even the attention function is asymmetric. So basically, the matrices in the equations are not symmetric. Yeah. So
yeah. So like for this over smoothing problem, so you can't actually deploy deep graph convolution networks because it smooths out. So there have been some attempts like you kind of use some residual connection or skip connection to kind of keep the information intact or like add more layers. So does it connect anyway to your work as well?
Yeah. So well, it's an interesting question. So basically, there are theoretical results and there are practical results, right? So in practice, you don't really look at the limit, so you stop the diffusion at some point. In principle, this kind of diffusion in the limit you get the enharmonic solution. So basically it's a vector in harmonic space that it's either constant or maybe in some other cases it's not constant. So you really do over-smoothing. There are other types of diffusion that do not necessarily lead to this kind of solution. The harmonic space is more interesting, and this is what we are trying to do. So when I alluded to results in algebraic topology, so there is an entire mechanism that is called sheaves, where you can have a more interesting diffusion that doesn't necessarily over-smooth. Now, when you allow for graph rewiring, everything changes, and I have not seen really any analysis because basically the diffusion analysis assumes that the domain is fixed. When the domain changes, then it might look differently. Also, the expressive power of such graph neural networks, where the graph changes on the fly, is probably stronger than the Weisfeld-Lemon algorithm. But again, this is an open question. I haven't seen any theoretical analysis yet.
Okay, so I guess we have one last question from Professor Dasgupta. Please go ahead.
Thank you. So, I mean, perhaps a simple question. So, I just wanted to get some physical intuition behind this Ricci flow, either the Ricci flow itself, or what exactly is happening to the graph properties when you are doing this rewiring. Is it that the graph is becoming more expander-like, or is it that you are isolating the communities? Is it possible to understand it in any sort of physical way?
Yeah, so probably the Ricci flow is not a completely fair way of thinking of it. It's actually a backward Ricci flow, or it's analogous to a backward Ricci flow. So Ricci flow, if you apply it to a graph, then it will do some kind of clustering. So it will disconnect communities, right? So if you start with this dumbbell, then the dumbbell will sharpen, and basically its topology will become two distinct spheres. So it will create a thin neck, and then it will disconnect. If you run the Ricci flow backwards, then it will homogenize the curvature, and everything will become looking like a sphere, and it will have a constant curvature. So this is what happens in our case. So we try to somehow make the curvature more uniform on the graph. So we don't want these few edges where we have negative curvature. So it becomes more constant.